Okay, lesson 3-5, the title is intervals increasing and decreasing, okay? So and we're not really going to work this solve and discuss it. I'm just going to use it as to talk about a couple of things with you, okay? It says Martin will ride his bike from his house to his aunt's house. He has two different routes that he can take. One route goes up and down a hill. The other route avoids the hill by going around the edge of the hill. How do you think the routes will differ? What do you think about the relationship of speed and time? So one of the terms that you will be introduced to in this section is the term an interval. And an interval is just a section of time on a graph that something is happening. And then when there's a change, that becomes a new interval. And then that will happen for a while. And then there's a change, that becomes a new interval. So if you look at Martin's ride, the first interval is this stretch where he leaves his house. Okay, that's an interval. And then the next interval would be when he goes up the hill. And then the next interval would be when he goes down the hill. And then the next interval would be when he flattens out again. Okay, there's 4 intervals to the over the hill part of his route. Okay. If you've ever rode a bike before, what do you guys think would be the slowest interval of the over the hill ride? Casey? What color? Red, blue, purple, or green? That's here. Well, that's this.
That is, it's like after.
Yeah, right here.
Yeah.
Okay. Why would that be the slowest? You're right.
Going up.
Yeah, it's going up a hill. If you've ever ridden a bike up a hill, that is no joke, right? Burn out your legs. So you know that you slow down and you're just grinding, trying to get up that hill without tipping your bike over. What would be the fastest portion? Somebody else. What would be the fastest portion of this ride, do you think? Essie? Yeah, going down the hill. You probably don't even have to pedal, right? When you're going down a hill, you just start flying. And then the red and the green section there on both ends, those are probably about the same. Okay, they're both flat, nothing really special about them. So you would guess that the speeds on those would be about right. What if, do lime green here, what if he decided to take this route and go around the hill? What do you think would happen with his speed on that entire trip? Micah? Okay, would it change much from the time he left his door to the time he got to here? His speed? Nothing really to slow him down or make him go faster. It's all flat. So would you guess his speed would be about the same throughout most of that? Okay. What about the distance? How does his distance change if he goes around the base of the hill? Corbin? Yeah, it's a greater distance. So do you want to have a up over the hill that's a shorter distance, but you're going to have that time where you're really going to be going slow, but then you're probably going to make up time going fast down the hill? Or do you want to take the more steady route, which is not a lot of change in speed, but a greater distance? Okay. And we're not actually going to calculate anything from this. I just kind of wanted to introduce intervals to you and talk about how going uphill and downhill can change your speed. Okay. All right. So go ahead and turn to the next page. And we're going to introduce a couple of vocabulary terms. So I'm going to actually skip talking about example 1, and I'm going to go to this step 1 and just talk about where it's highlighted in yellow. It says qualitative graph. That is a very, very fancy term for basically a generic graph. And what I mean by that is we are used to seeing graphs that are like 1, 2, 3, like we're used to seeing numbers, right? And we're used to seeing distance, 10 miles, 20 miles, 30 miles. And so we're used to being able to look at this and saying at this point, right, they've been riding 3 miles and they're 20 miles from where they started. A qualitative graph is just without all the numbers. We can't really be specific. What we can say about this graph is that this train started here, right? Because we know that's our start point. And after some amount of time, they went a distance. We don't really know how far. And then there was a change. How do we know there was a change? What changes between that first section and that second? Yeah, exactly. The slope is steeper. So from this interval, or from this point to this point, this purple section, okay, that's one interval. And then the blue section is one interval. And why we have a break, or why we say there's one interval and then a second interval, is because our steepness of our slope changes. And in this case, because of the graph, we have distance over time. We know that distance over time is what? What does distance over time equal? Think about 50 miles in 1 hour. What is that? On the highway, what kind of a sign is that? Yeah, speed. When you have, and this is very specific, but when you have a distance, and how do I know this is a distance over time graph? Well, because I have the word distance here, and I have the word time here. So I know this is the distance over time, right? And y is always go on top, which is why it's distance over time. My y's always go on top. Distance is my y, right? Distance is my y. Whoops. Keep that colored, right? Distance is my y-axis. Time is my x-axis. Distance over time, and we know that distance over time is speed. So what this graph is saying is that in the blue segment, this train was going some speed. We don't know exactly because it's a qualitative graph, meaning we don't have any exact numbers. We can just tell kind of a generic story. And then in the purple section, the train does what? What's the change? What change happens between the blue and the purple? The slope is steeper, which means the train did what? Think about their speed of the train. What would a steeper slope mean? Yeah, it's going faster. So very generically speaking, we can say that this train started out at a certain speed, and then after the first interval, the train sped up and went that speed. Now, would I say that the speed between the two purple points is a constant speed? Why would you say yes? What is unique about this purple section that would make you think constant? Straight line. Beautiful. It's a constant speed because it's a straight line. So the blue section is a constant speed, right? I meant to do a pen, not a highlighter, but that's all right. The blue section is some constant speed. I don't know what, but it's a constant speed because that little segment is straight. Then there's a sharp bend in that line because the train changes speeds. And for this whole purple section, the train goes another constant speed, but it's faster than the blue section. Okay? That's pretty much everything that all of the words on this page are talking about. Just as a reminder, and we've already talked about this in the jump start, but the X, right? The X is always the input. Think about the ingredients, right? The ingredients that go into the equation that spit out a Y. And the Y is always, the Y is always the output. You put in ingredients, you put in X's, and run it through the PEMDAS machine, and it's going to spit out Y's. Okay, think about your Hershey Kiss factory. All the ingredients are your X's, your flour, your sugar, your cocoa, all that good stuff. No, flour doesn't go in chocolate. Ew. Your sugar, your cocoa, your butter, all that good stuff. Those are your ingredients. That's all your X's. Run it through the PEMDAS machine, and it's going to spit out little Hershey Kiss Y's. Okay. All right. How you would describe a relationship. Okay. This is on your homework. So I want you to put a little star next to this right here. Okay. Where it says step 2. Says determine the relationship. So in your homework, you're actually going to have to describe the relationship. Here's what I want you to really note about describing a relationship. Okay. Put a little star here. Use both axes by name in your description. And when I say by name, remember last week when I said you can say generic boy and girl, or you can say Corbin, Maddie, right? The generic is the X and Y. The name is the actual name of the axes. So use them by name. So that means don't just say as the X-axis does this, the Y-axis does this. For this particular graph, you're going to say as time does something, distance does something. Okay, that's what you're going to say. As time, fill in the blank, distance, fill in the blank. That's how you describe a relationship. If you just talk about the distance, or you just talk about the time, it's an incomplete description of the relationship. Okay, think a relationship, it's two people, right? Can't really be in a relationship with yourself. You got to have two parts. So when you're describing a relationship, make sure you're describing both axes by name. And in this case, if I describe what's happening in this second interval, time always, can you go backwards in time? Okay, time's always going to increase, right? So as time increases, distance increases. Actually, I don't want my arrows doing that. I'm talking about distance, which is the x-axis, so or the y-axis going up and down. So when you would actually write this out, and they've done it for you, you don't have to do it. I would just maybe put a star next to it as an example. As time increases, the distance the train traveled increases. That's describing the relationship. So whenever your homework says describe the relationship, that's what it's asking for. As fill in the blank, time, because that's the name of your x-axis here. As time increases, distance the train has traveled increases. It may not always be time and distance. Okay, look at this example. This one's time and speed. Okay, so if I was to describe this relationship, I would say as time, again, time always increases. Speed, I'm not going to use the word distance now. Why not? Because this isn't a distance graph, it's a speed graph. Every graph is going to be different. You have to look at the names of your axes to be able to know how to answer these questions. What happens to our speed? As time increases, what does our speed do? No, look at what your speed does, Miss Borden. Yes. I'll let her know. Thanks. Maddie, you're leaving. So you'll probably want to go watch the last maybe 5 or 10 minutes of this video just to get the rest of your notes and be able to do your homework, okay? Okay. Think about if I were to just put some random numbers in here just to help make it make more sense. If your speed is 0 here, and just say your speed up here is 30, and I'm just putting random numbers in here. What's my speed doing? Always read graphs left to right. Yeah, it's decreasing. Now, this is a qualitative graph, so I was just putting those numbers in there just to kind of put something in there to help make it make sense. But we don't know the exact speed, but we know the speed as time goes on, the speed gets lower and lower and lower and lower. It's decreasing. So the sentence that you would fill in to describe the graph would be as time increases, the speed of the train decreases. And so this function as a whole is decreasing. As time increases, speed decreases. Okay, that's how you're going to explain it. And again, what did we use? We used the word time. We used the word speed. You always want to use language from your graph to explain the relationship of your graph. Okay. In describing a relationship, don't ever just use generic X and Y. Don't just say as X does this, Y does this. Name them based on the graph, name them how they name them. Okay. How would this graph of the function change if the speed of the train was increasing? Very difficult, I know, but I have faith in you all. Are you ready for this? That's what it would look like. That's it. Okay. The blue section shows the train decreasing in speed. The green section that I just added would be an example of showing the train increasing in speed. Okay, because, right, I went up as time goes on, because my time keeps going, right? My time keeps going. As time keeps going, I now have my speed increasing. Okay. All right, are we good with that? All you got to do is know the difference between increasing and decreasing. So far, so good? All right, how about a non-linear function? These were linear, right? Straight lines means constant. Okay, what about nonlinear? This gets a lot harder. Are you ready for this? Super duper hard, but I have faith in you guys. This section is increasing. This section is decreasing. That's it. Doesn't change. Okay, is it going up or is it going down? And you always read left to right, whether it's straight or whether it's curved or whether it's a little bit of both or whether it's squiggly lined. Just look at each interval. How did I know? Well, because besides the fact that they told us that this was an interval and this was an interval, it's because that's where something changed, right? That middle part right here, this is where something changed. That makes the red one an interval. And then there's a change happening, whether it be the distance changed, right? The height changed, the speed changed, whatever changed, that becomes a second interval. Okay, most of the time they'll tell you what's an interval and what's not. But if you need to section it off yourself, just look and see where something changes. Okay. All right. Try it. It says this graph shows the behavior of Skyla skateboarding at a skateboard park. In which intervals is the function increasing, decreasing, and constant? So let's start with where is it increasing? What intervals are increasing? 1, 2, 3, or 4? Eli, what do you think? 3. Perfect. Okay. Now let's look for decreasing. Jacob, where is it decreasing? And good. 1 and 4. Those are the 2 spots where it's decreasing. This is something we haven't really talked about, but where is it constant? It's not going up. It's not going down. Dayton, what do you think? Which interval? 1, 2, 3, or 4? It's not going up. It's not going down. Good. 2. Okay, not going up, not going down, staying flat. Now, flat means 2 different things. Okay, and I want to cover that with you. It depends on the name of your axes. So in this particular graph, we're talking about time in seconds and distance above ground in meters, right? A distance above ground in meters. So if I was to ask you if I was to ask you on the y-axis, what does this right here at the base, what does that stand for? If it's distance above ground, what would base level be? What would the 0 be? At 0 meters above ground, where are you at? Specific to this story. If I jump and I jump 0 meters above ground, where are my feet still? Which would be what? In words, not numbers. On the ground. Beautiful. So if this is distance above ground, you got to know that at 0, that's the ground. Okay. And what this is saying is that in interval 1, right, you start off way above ground and you go down. Where are you at interval 2? Dalton? On the ground. Yeah, in this particular story, and it's going to change every story, but in this particular story, you're on the ground, and you're on the ground this whole interval, and then you rise up again, and then you fall again. But a flat spot, depending on if it's a distance graph or a speed graph, a flat spot's going to mean something different. Okay, and we'll kind of get into that. I'm leading into example 3. All right. Example 3, describe the relationship of quantities. In which intervals is the function increasing, decreasing, or constant? It really is as easy as this. And I'm not being funny or flippant. It just really is as easy. Increasing, right? Increasing is 1 and 3. It's where it's going uphill. Okay. Constant is where it is flat. Okay, so constant is 2 and 4. Those are the 2 spots where it's flat. And then decreasing is where it's going downhill. So when you're asked to identify what is happening at an interval, you're either going to use the word increasing, decreasing, or constant. Okay, now this part we'll just kind of have a little fun with. Write a scenario about the graph or about what this graph could represent. All right, so we're going to write us a little story. First of all, I need a person's name. Who's in our story? Casey? Sally. All right. Sally is, where's Sally at when she starts? Right here. Where's she at? Any place in the world. Where's Sally at? Walmart. I like it. All right. So Sally is at Walmart. All right. Now, notice on our graph, what's what? Okay. Notice what's what? This is distance. So in this particular graph, she's going a distance away from Walmart, right? Over some amount of time. And it's a qualitative graph, so we don't even know the exact time and distance. We just know she's doing something. All right. Sally is at Walmart. Is she walking or driving? I don't care. What do you guys think? Corbin? She's walking. All right. Sally is at Walmart. Okay. She walks to, all right. Where's her next stop? Where's she at? Somebody tell me. Where? Subway. All right. She walks to Subway. Okay. So Sally is at Walmart. She walks to Subway. Okay. And we don't know how much. So we're just going to put some distance from Walmart. I don't know how far because it's a qualitative graph and I really don't know. Some distance from Walmart. All right. Now this is where you got to think about what a flat constant spot means. Okay. Think about this. This is distance from Walmart, right? If she's this amount of distance from Walmart at the beginning of the segment, and she's the same distance away from Walmart at the end of that interval, what was she doing at Subway for that amount of time? Was she still moving? Was she still getting further away from Walmart? Was she getting closer to Walmart? She was what? Yes, she was stopped. She was staying still. She stayed at Subway during interval 2, okay? Because her distance didn't change. She didn't get further away from Walmart. She didn't get closer to Walmart. Her distance stayed the same. So she walks to Subway, some distance from Walmart, and stays there. We don't know how long, but we know she stays there. All right, now she takes off again. Where's she going next? What's her next stop? Corbin? Save-A-Lot. All right, she's still doing a little bit more. Save-A-Lot. All right, she's at Save-A-Lot. So she then walks further from Walmart, right? She gets further away. Her distance from Walmart gets bigger. She walks further from Walmart to Save-A-Lot. All right, again, think about what's happening in interval 4. Where is she at for the entirety of interval 4? She's at Save-A-Lot. Her distance to Walmart doesn't get bigger, doesn't get smaller. She stopped, right? So then walks further from Walmart to Save-A-Lot and stays there. And again, we don't know how long because it's a quantitative graph, so we don't know. All right. What happens in interval 5? She goes where? Almost. Where did she start out at? Where does she go back to? Yep, this whole interval 5, she's going back to where she started. And in our story, she started at Walmart. So she then goes, or let's say walks, because we were specific about how she got there. Then walks back to Walmart. All right, we just wrote a story. Okay, it's not hard to do if you just pick it apart by each segment. Okay. All right. Remember in key concepts, this is just really quickly. Remember that increasing is an is a description of going uphill. Constant is a flat spot. And then decreasing is going downhill. Those are the 3 terms that you're going to use to describe movement in your intervals: increasing, decreasing, and constant. And I want to show you one thing that will help you with your homework. Notice what is different about this graph and what we just did with Sally walking to Walmart, right? What is different about this graph? We still have time. What's different? Caitlin? Well, there's 2. Well, there's actually 3 constant spots. Corbin? Yeah, it's speed and not distance. Why does this matter? Well, because remember in our distance graph, a flat spot meant your distance isn't changing, meaning stopped. But you think about this, if you're traveling and your time is, right, your time is increasing, right? Time is increasing. In this first interval, what is increasing? Speed. Speed is increasing, right? What is happening here? Are we stopped? Think about I mean, you can just put any arbitrary number in here. Let's just say this is 30 miles an hour. Are we stopped? Yeah, you're using your cruise control. So see how it's different. A flat spot in our distance graph meant they stopped at Subway, right? But a flat spot on a speed graph doesn't necessarily mean stopped. It means they're using cruise control, right? They're going the same speed consistently for that whole interval. Then they do what here? They slow down. We have another flat spot. What could this flat spot mean? Why stop? This flat spot does mean stop, but not because it's flat. It's because they're at 0 speed. So with this flat spot here, let me get one more color here. Would this flat spot here mean cruise control or stop? Are they cruising at 0 miles an hour? Think the speed. Think about if it helps you to fill it in, do it. This is 0 speed. Put arbitrary numbers in here. It doesn't matter what you put. Sometimes it helps you see it, just to pencil in a number just to give you a visual. Would this one up here, would that be using cruise control or stopping? Yeah, because they're going at, I just said as an example, 20 miles an hour, but they're cruising along at the same speed, but it's not at 0 speed. So in a speed graph, a flat spot can mean stopped, or it can mean using cruise control. How about this flat spot right here? Cruise control or a stop? Yeah, cruise control, just a little bit slower than our other cruise control. So when you're writing out what's happening at each interval, you need to write out, right, what might the constant intervals in this function represent? Well, you need to number them. You've got 4 constants here. So let me just kind of set you up for your homework here. You've got 4 constant intervals. You've got one here, you've got one here, you've got one here, and you've got one here. You need to say what's happening at each one. At the first constant, what's happening? At the second constant, that one's kind of unique because it's all the way down at 0. And then at the third and fourth constant. Okay? All right. Your homework is number 6 through 10 on page 199, and that is it. Okay? And let me know if you have any questions.